Hello. Having discussed about the force acted upon a moving charge by an external magnetic field, especially when the field is normal to the charge tends to move in a circular manner on a plane to which the uh, field acts normally, and also the case when the charge is projected out of that plane at a certain angle with respect to that given field acting normally to the plane, the path taken is helical. But we are more concerned about the initial case where the charge tends to move in a circular path along the plane, and we use that concept as I had mentioned in case of cyclotron. So let's discuss the cyclotron at in gist, and we'll get to know about a summarized view of what exactly happens. Now, cyclotron is a particle accelerator. It accelerates charged particles. Neutral particles cannot be accelerated by it because the neutral particles obviously cannot be acted upon by the force due to the external magnetic field. So this is a particle accelerator. It accelerates the particle along a circular path, and that's why the uh, cyclic electron or proton uh, results in the cyclotron. What it has, the particle acceleration does take place in a linear manner as well. That's mostly in case of much lighter particles that are there. Um, the elementary ones, the particle accelerator being at CERN, Geneva, is a linear accelerator, whereas the cyclotron is for a small space. As you know, that Large Hadron Collider occupies a much bigger space. The cyclotron, on the other hand, the cyclic way of projecting a particle to a target. What it does essentially is that if we have a charged particle, it uh, it is acted upon by a magnetic field, and it tends to spiral, and it gradually accelerates with the centripetal acceleration that it achieves, and gradually it is projected out to a target to which it was intended to strike, and that target, in order to achieve some experimental result, of course. Now, this is more or less the case that happens with a particle accelerator and in case of cyclotron. Now, the cyclotron device, the structure or the construction of the cyclotron is such that im- it applies both the electric and the magnetic fields for the charged particle. So this is more or less the diagram that I'm going to show you. It consists of plates in the shape of Ds. So this is one of the Ds written in the laterally inverted manner. This is a D, and this is another D with a spacing in between. So if you add those two Ds, they comprise or constitute a circular disc. So these are the two Ds that we have. They are equal in shape, symmetric mostly. Uh, my diagrammatic uh, errors may lead to some different kind of structure, but more or less this looks like D. So in those Ds, what we get is that we place the particle to be accelerated. Suppose we have a positively charged particle. Let me take another ink for showing you the particle over there. So we have a positively charged particle, suppose, and it is these two Ds, they are somewhat the shape of hollow discs, just like this. Let me give you a cross-sectional view of it. So this is a disc. This is one of those Ds that I'm showing. So this is an opening of that D, and this is how it continues. Okay, so this is how it continues. A three-dimensional view of it. So this is a small shape that I've taken. This is more of like the case of the Oreo with the outside cover on and the cream missing. So that is more or less the analogy that I can draw. And from that analogy, what we get is that these two Ds are connected to an alternating source, and as a result of that, at one point of time, this probably has a negative charge and this has a positive charge, and it is set to the on state. And what happens then is that this particle, this positively charged particle, is attracted into this D, and what we also do is, the most important thing is that we place it in a uniform normal magnetic field. So this is the normal magnetic field which acts. So they're basically placed between two magnetic poles. So now what happens is that as the charged particle is attracted into that slot or into that D, it continues in that path and it takes a parabolic path, because as we have understood, this will take a parabolic path, and by the time it completes its path and it reaches here, at that point this cycle will reverse and this will become positive while this will become negative. And exactly at that time, with that becoming negative, this will be attracted into this D, the second D, and the process continues when the field acts normally, and this charged particle tends to travel in that circular path. Now with equations we can prove that gradually tends to spiral into a bigger path, and the change or the alternating source is changed accordingly, and as a result of that it takes a circular path, it continues, and then it is provided with a certain window so that it goes through that window and strikes the given target. So it is more or less like that. So that is what we had presented over here without the D's and the external circuit and the magnetic field. So this is more or less the idea that is involved in the acceleration of the charged particle by a cyclotron. Now we have the equations that are associated with, or that support this kind of trajectory of the charged particle, and that we had discussed previously. What we had ended up with is that for a charged particle we have the time period and the frequency, with the frequency being equal to qb divided by 2 pi m. Now q is the charge, b is the magnetic field that is being applied normally, and m is the mass of that particle. Now the charge remains unchanged even if it acquires a greater speed that is nearly relativistic speed. Now what about the mass? Well, the mass supposedly achieves a value m being equal to m naught 1 minus v square by b square, v square by c square under root, that is the rest mass, that is the relation of the relativistic mass. This is the relativistic mass with respect to the rest mass, which means at velocities comparable to the speed of light, the mass increases as opposed to the initial rest mass that the particle possesses. So in that case, with this increase in this value of the mass, the frequency may decrease, but we are concerned at maintaining the frequency of these cycles that are taking place from the positive to the negative, negative to the positive, and back to the negative or back to the positive. So we wish to maintain the we wish to synchronize the system so as to obtain the results accordingly. And that is why what we do is we can vary the field externally, that is we can go up a bit by changing or increasing the value of b, and in the process we can synchronize the cyclotron, the motion of the charged particle within the cyclotron. This is more or less known as the synchrocyclotron. Synchrocyclotron, in which we obtain such a result where we synchronize the, even with that we can also synchronize the AC source with respect to our requirement with respect to the motion of the charged particle, so as to obtain the desired result. So any kind of synchronization involved can be maintained or can be done according to the calculations that are available to us. So this is more or less the case of a cyclotron, where a charged particle is accelerated uh, and then it is allowed to strike a given target for carrying out experiments and obtaining the results or studying the results. Now let's move over to the case where a current carrying wire or a conducting material is acted upon by a certain force when it is in the presence of an external field. Now we know that a moving charge experiences a certain amount of force when it is subjected to an external magnetic field. Same will be the case in case of a current carrying wire, because the wire ultimately carries the moving charges within it, especially in case of the solids, that is we consider the case of electrons moving, and that is the negative charge, and when it is subjected to some external field, it will definitely acquire, or it will definitely be acted upon by the magnetic force or force due to the magnetic field. So let us consider that. Now this is supposedly a wire carrying current. Now the wire carries current along that direction as shown, and that direction, that means we will assume the direction of current to be in the direction of the positive charge rather than taking the electron in the opposite direction. It's all the same thing. So the positive charge moves along that line, and supposedly the magnetic field is acting along this direction. Then we have a certain angle between them, let that be equal to theta. Now along that length of the wire, that means the charge is moving along that direction, what we are going to get is simply an expression. Now we know that for a given charge dq, now let us take a small segment of it, which is of length dl, and that carries an equivalent charge of dq, where dq is obviously the small amount of charge within that dl. Now that dq is going to experience some force df, which is equal to dq, and it is moving with a velocity v cross b. Now that v is in that given small interval of time that we may consider. We are considering infinitesimal cases for our convenience, so that is why, for obtaining better results obviously, so we have dl divided by dt, which means that length dl, that infinitesimally small elementary length dl, over the time dt is going to give me the velocity cross product with v. I can afford to take that dt out, so I am left with dq by dt on the outside, and dl remains as such. So now I have dq by dt, which is giving me the instantaneous current, which is I, that has been shown in that figure, and we have dl cross b, sorry. So we have the force to be acting with relation to that uh, length as well as the current flowing through that wire. So the total force can be calculated provided we know the total length according to the given conditions, and we have the force to be equal to IL cross B, where L is always directed along the direction of flow of current. Remember, current is a scalar quantity, but we are taking the length of the conducting wire, so that length gives the motion of the charge, positive charge, and that is why there's no problem with that. So this is another form of that QV cross B that we had discussed earlier. In this case we are considering the length as well as the current that is flowing through it. So the same thing interpreted in a different manner with the conductor and its parameters available to us. Now we had discussed QVB. Let me add a term which I hadn't added previously because we were not involving the electric field over there. So now is the time to use that term, which is known as the Lorentz force. And the Lorentz force is the complete or the resultant force that is acting on a charged particle when it is subjected to both the electric and the magnetic field. So the resultant force is known as the Lorentz force. Let me denote it by FL, and that is equal to the force on it due to the electric field and the force on it due to the magnetic field. And as we know, for a given uniform electric field acting upon a charge q, we have q times of E as the force due to the electric field, and as we have learnt in the previous video, that we have the force on that charged particle moving with velocity. It must be moving, because if it is not, then it is not acted upon by the force due to the magnetic field. So QV cross B is the force in that case, and that is why we have the Lorentz force to be equal to, we can take the Q out, so we have E and the vector sum of E with the cross product of V cross B, giving us the Lorentz force. In the absence of the electric field, however, the Lorentz force is only going to involve the force due to the magnetic field, and in the absence of magnetic field, the Lorentz force is involving only the electric field, force due to the electric field. But it's not the case. Mostly it is used in case of the magnetic force, and that is why in absence of magnetic force it becomes purely electrostatic force with no motion involved initially for the charge. Now, having learned about the force on a conducting wire, we may well be interested to consider the case where the field of one of the wires is affecting we know that a current carrying wire can possess a certain field to be associated with it. We have learned that right away from Oersted's experiment through and the application of the Biot-Savart's law. So there is always a magnetic field associated with a current carrying wire, and that field might affect the wire which is placed nearby and carrying a certain amount of current, and therefore a force may be may be created between them. So let's check for that if there is any kind of possibility in that case. So force between two wires carrying current. Now we'll consider the easier approach where we consider the parallel and the anti-parallel cases. Then we can move over to the other possible ways in which their orientation, possible other orientations of those wires, so as to obtain different expression, if any. Now here we have two wires, that is the parallel case, placed parallelly. Placed parallelly, which means they are carrying the current along the same direction. So these are the two wires, and supposedly they are separated by a distance a. Now this wire, let me name those wires. This is the wire 1, this is the wire 2. They are continuing, they're straight wires, they are continuing throughout their lengths. We have no restriction with their lengths as of now. And this is carrying current I1, suppose, and this is carrying a current I2. And this I1, as you can see in the upward direction as it moves, with the techniques that we have learnt, we can say that the field due to that on the wire 2 will be into the plane, and this will be into the plane, and this is a B1, that is the field due to the first wire at a point on the wire 2. Similarly, considering the case where the current I2 goes upward in that figure, the field due to I2 on I1 will be out of the plane and acting like this. So it can be represented by a dot encircled as per the vector notations go. So now with these two wires, with these two fields available to us, let's just obtain the relation or obtain their formulas. So B1 is the field. We are concerned about the magnitude as of now. We know the directions pretty well. So B1 is the force, or is the field of the due to the current of the first wire on the second wire, which is placed at a distance a, perpendicular distance a. So this is mu naught I. I'm writing it in another ink for you. So B1 mod is equal to mu naught I1, because that's the current which is resulting in that magnetic field, divided by 2 pi, distance being a. Now remember, as I had mentioned, that these wires are really very long, so we have the special case of infinite length over there. Infinite as in case of this being incomparable lengths, not exactly infinite, uncountable or something like that. B2 similarly has somewhat similar situation where mu naught I2 is the current that creates that magnetic field over a distance, perpendicular distance a. So these two are well known to us with the directions present over there. Now let us say F12 is the force on 1, that is on the conductor 1, due to the field of 2. So the field of conductor 2, that is B2, applies on the wire 1. So that means F12 will be equal to I2, which is the current that is being carried by the the current that is carried by the first conductor. Let me erase that. So we have I1, the force, the first conductor, and it is acted upon by the field. So I1, the length, let us take the length for now to be L1, we'll do away with that later, cross B2, that is the field of 2, as I have written over there. So I1 L1 cross B2. Similarly, we have F21 to be the force on 2 due to the field of the first conductor, that is field of 1. So we have F21 to be equal to I2 L2, let its length be L2, again we'll be considering that later, cross B1. Brackets are always important, let's put them. Now on the left hand side, with the cross product for L1 cross B2, we know B2 is out of the plane and L1 is directed along the current. So applying the right hand thumb rule, you can very well see that the force is going to act along that direction. That is, F12 will act along that direction. Force on the conductor 1 due to the field of 2. Similarly, if we are to see for F21, I2, L2 is along that direction of I2 and B1 is directed into the plane. So L2 cross B1 is going to give us, from the right hand thumb rule, we are going to get just the cross product of vectors, so that's no big deal. So F21 is going to be in that direction. So both these forces are directed opposite to one another, towards one another, which means they will be attracting the wires. That means the wires will start to get attracted towards one another, thereby constricting that path between them. Now, as I had said, that the length is not that mandatory over here, because the lengths must not be considered with those huge distances. Take for example the wires drawn along the streets of the wires carrying current drawn along the streets on those poles. The wires, they continue to carry current and they continue throughout the length of the street and throughout very long distances. So in that case the length is immaterial, and so what we do over here is that, considering the magnitude, in this case we have I1 L1 and B1 of the value, B2 of the value mu naught I2 divided by 2 pi a. We can divide the L1 over here, so F12 divided by L1 is going to give us mu naught I1 I2 divided by 2 pi a, and we may well take this as a small f12, and we are considering the magnitude of it. We know that both those forces, so this is the force per unit length. This is the force per unit length for the first wire, that is force acting on it divided by its own length. And similarly on the right hand side, what we do is we take the force per unit length considering the magnitude only. So here we have I2, then L2, which is to be taken on the other side, and for B1 we know that it is mu naught I1 divided by 2 pi a. So finally over here as well we have mu naught I1 I2 divided by 2 pi a, and the L2 term can go down, and we therefore end up with f, small f 21, that's the force per unit length. And if you observe, the magnitude is exactly the same as on the left hand side. So These two forces per unit length, they are equal and they are opposite. They constitute the action and the reaction forces. So that is more or less the case when the wires are carrying the current in the parallel direction. What happens in case of anti-parallel direction? Well, in case of the anti-parallel case, in that case, the one of the wires, if this one is taking it upward, let's take this one in the downward direction. And the field due to the first wire on the second is acting into the plane. But now, due to the second wire on the first wire, now this is B1, of course. This is 1, this is 2. And now B2 also acts into the plane as far as the direction of the field is concerned. So this is B2. Now, if you were to take the cross product, L1 cross B2 is going to give me the direction of the force will be along this direction, that is F12. And similarly for L2 cross B1, if you take it, it is going to be in this direction, that is F21 will be. Now they are still action and reaction forces because they are equal and opposite when considered as force per unit length. The mathematics is exactly the same, there is no difference in that, but the thing is that these are now repulsive forces, they repel. Whereas I'm not going to repeat the mathematics for sure because it's the same, exactly the same. You can try that by using those laws, and this they attract. This happens in case of lightning conductors if they are in the form of poles, hollow poles, and they are you know they are added to that building of tall towers, skyscrapers mainly. So in that case, the lightning, as it strikes those poles, by the time you see them, those poles being hollow, they are somewhat like this from the top view. And as the current strikes these poles, the segments of these poles will carry the current along them, denoted by those cross that I have drawn over there. And that means all the currents will be going parallel to one another. So these two will attract, these two will attract, these two will attract, and as a result of that, the pole gets constricted to some extent like this. The shape of the pole changes, it gets constricted, it drags itself inwardly, and you end up with this kind of shape. The opposite sides have attracted one another, and as a result of that you end up with this kind of shape. uh, the top shape, and gradually downward the distribution is almost the same. So this is one of those examples that we see. They do not use these hollow poles in most cases. In case you have a hollow pole, cylindrical pole, this is conducting, of course, this is what you end up with on those once those lightning strike, once one of those lightning strikes it. Okay, this is all we were to discuss in today's video related to the magnetic effects of electric current and the moving charges and the current under the influence of the magnetic field, that is. We'll be ending this segment in the next two videos, so stay tuned for that. Till then, thank you for watching.